Hey, how are you?
Hello, I'm good. How are you?
Good. Is it snowing where you are? Or did it snow?
It did snow yesterday. It was like maybe an inch, and
Same,
then it stopped.
same. All right.
Um,
Yep.
no, I wasn't missing anything.
Okay. So yeah, what's new?
Um, a lot and nothing at the same time. Um, I so like after our session, I studied like the day or two after, and then I got sick, and then the holidays happened, and I kind of just lost a lot of motivation
Got
in
it.
like the past 2 weeks. So
Uh-huh.
I like did not study at all, basically.
Got it.
Like I did all of the Jack Weston like diagnostic questions
Yep.
um like within the last couple of days, and I've been reviewing those, and I still have to make like Anki cards for the ones that I got wrong, and like thoroughly review all the content. But I don't know. I was like kind of disappointed that I lost a lot of motivation, and like I feel like it was kind of a setback from where I was before.
Mhm.
But
Yeah.
yeah.
Yep. So yeah, it doesn't seem like it's a holiday, so you know, you're gonna people are gonna spend that with their families and stuff like that. So all right, cool. So you did the Jack Weston content diagnostic, and yeah, we can go over stuff from that if you'd like.
Yeah, I did biochem first, and I let me like double check because I'm looking at Chem Phys right now, but I'm pretty sure I got a 70% on the biochem. Um,
What about for CB?
for CP, I got 66, which like honestly was kind of higher than I thought I was gonna get
Yep.
because I'm like really, really weak in chem physics.
Yeah.
And then for Psych. Sorry, I just have to find it.
Mhm.
Yeah, I got an 80 something on it, but I need to double check because I can't find it right now.
Sure. So yeah, I think we can go over like the CP stuff. And I'm looking at the document you sent me with practice questions. Um, is there anything here that you want me to look at in particular?
I was so I made like a little checklist of the ones that I needed help with the most. If you scroll to the right, it's under the like help section, and the I can like show it to you on my screen. It might be easier for me to explain it, but it goes based off of like the questions. It's most of the questions that I had issues with were more like math, like applying a concept mathematically,
Yep.
like understanding what equations to use.
All right.
Um,
So is this the CP Orgo like tab?
yeah,
Okay.
it's the CP Orgo tab, and then if you scroll all the way to the bottom, the most recent like section under the black line.
Hmm.
And then I found the psych and sociology, and I got an 81 on that.
Got it.
So like there's still areas I want to improve on, definitely in both like all three categories, but I think and Phys right now is the worst.
Got it.
And then the first question I had, let me check. Are you able to see like the diagnostic questions on your end, like on the Jack Weston website, or do you want me to share my screen?
Oh yeah, you could share your screen.
Okay.
Yeah.
Right. Okay. Um,
Yep. Go to detail. Yep.
slide 29.
Oh, you can just go all the way up top.
Oh,
Yep. Yeah, if you go up, if you do it from the thing on the top, then you can have it display all the questions.
oh, that's a
But
lot easier.
two.
But I guess for now I
Yeah,
could
this
just
works. Yep.
click through.
So
Okay. It was this question about enthalpy of formation. I like kind of had
I think
it
you forgot
right.
to put the two, the multiple.
Well, that's like what I was confused on because like in the correct answer explanation, the two was with the x, but wouldn't like why wouldn't you multiply the 554 and the 634 by two? Because they have the coefficient on them.
Well, that's what they're doing, right?
Well, aren't they multiple? I was just confused on like their explanation for it. Maybe I was looking at it wrong.
So the X here is means multiplication.
Oh, it's not a variable?
Correct, yeah.
Oh God. Okay. Because
Well,
I thought they were using like the O2 from the equation and they were um like you had to do something with that.
so um okay. Yeah, so see how these values are kilojoules per mole, like the units,
Yeah.
and we need our answer to be in just kilojoules. So we would have to multiply kilojoules per mole by moles, right? For it to cancel.
Yeah. I think I just like originally I thought they were using X as that was
Uh-huh.
stupid. Okay.
So,
Okay.
yep.
I could skip that one then.
Mhm.
Let me see. Okay, I have issues with free body diagrams, I think.
Yep.
So the first one I was gonna ask to go over was this one.
Okay. So this is a topic called um, simple machines.
Mhm.
And what simple machines let you do is it lets you. So, do you remember the formula for work?
Um, Force times distance times cosine theta.
What do you think that cosine theta part is for?
It's for, I guess, like having to break up the x and the y components.
Kind of. So, um, do you remember like values for like cosine and sine? Um, like let's say cosine of 0 degrees. Do you remember what?
Oh, um, cosine of zero is one, I believe.
Good. What about what at what angle will cosine be 0?
90 degrees.
Good. And what about sine?
Sine, um, sine of 0 is 1, and then sine of,
Cosine
or sorry,
and sine,
sine of 1 is 0.
sine of one.
Um, Hold on.
Let's do this. So sine of 0 and sine of 90.
Sine of 90 is 1, and then sine of 0 is 0.
Because if you remember, like the sine curve is like that, and the cosine is like kind of like that. And here is 90 degrees. So if I zoom in on that, whoops, like 0 and 90, and this is 1. Sine, like as we go from 0 degrees to 90 degrees, sine goes from 0 to 1, and cosine goes from 1 to 0.
Okay.
So now this is important because the cosine value, you want it to be 1 to maximize the work, right?
Yeah.
So if you had, let's say this is a box and you're pushing it, so you're applying a force in this direction, and it moves a distance or displacement in that direction. What's the angle between the force and the displacement here?
0.
0, right? So, in other words, if the if the force and the distance are parallel, right?
Then if they're parallel, then cosine theta will be 1.
Yep. So like the 0 degree angle between the two indicate that force and the distance here should be parallel, right?
Yeah.
So another way of writing this would be FD, but a subscript. So this subscript doesn't mean 11, it means parallel.
Okay.
So now, whenever I talk about work, I also talk about torque. You remember that formula?
Um, is there a sine theta in there?
Yep.
Um, I don't know. Is it like R or FR sine theta?
Yep.
Okay.
So at what angle would sine be maximized, aka, you know, a value of 1?
At 90 degrees,
Right?
short perpendicular.
Yep. So I could also write this as FR. This subscript means perpendicular.
Hmm.
Okay. Now, let's say we have, or how about this? So if you a regular door, um if you open like a regular door, um how much work are you doing?
Um, well, you're putting force on the door.
Uh-huh. So like let's say this is the hinge, this is the door, and this is the knob, and you're applying a force, let's say to like push it open in this direction. And this is the length of the door, which is R. And what's the angle between the force and the R?
90
Okay.
degrees.
So how much work are you doing here?
Just like F times R.
So you could use like the work formula.
So,
So
okay.
yeah, what's the angle between the force here and the distance or the R?
Oh, so it would be cosine 90, so you're not doing any work.
Yeah, exactly. Cosine 90 is 0, so you're not doing any work. And but you are doing torque, okay? And torque is essentially the same thing as work, except work requires the force and the distance to be parallel, whereas torque requires the force and the distance to be perpendicular. And the reason we call the distance in torque R is because torque produces a rotation. And so if this rotated, it would be the radius of a circle, right?
Yeah.
Okay. Now, let's say you have a sliding door, right? How much torque are you doing there?
Um, you're not doing any torque because you're not rotating.
Yep. Because if you're pulling it open or close, uh, the force you apply is perpendicular to the door itself, right?
Hmm.
Good. Good, good, good. Okay. So yeah, so this is a fundamental kind of concept here, and you'll see um whenever you see like oftentimes when you see a cosine term, it'll mean that you want the angle to be like 0, and when you see a sine term, you want the angle to be like perpendicular or 90 degrees, right?
Okay.
So, yep. So, okay. Now, um, okay. So for this question here, they have like, okay, so there's a parcel, like a box, let's say, that's 1,000 newtons. And if you lift it, so this distance d here is 1 meter, right?
Yeah.
Now, if you lift it straight up to bring it here, you are doing some work, right?
Yeah.
And what can be the value? So, like, we would plug in what, 1,000 newtons?
Times
Mhm.
1 meter.
So 1,000 Newton meters. Now, uh, Newton meter could also be a unit, like could also be which unit?
Uh, joules.
Joules. Yeah. So there's also the work energy theorem, and that means that, like in physics, the definition of energy is the ability to do work. So in physics, we can kind of equate work and energy. In
Okay.
this case, this is like a gravitational potential energy, right? So, okay, so that's the work it takes. Now, one second, I'm showing up. Okay, so um okay, so if you use this ramp uh that has a length of 5 meters, you are still like your starting point is still the same as if you were not using the ramp. And the end, like where the box ends up, is also the same whether or not you're using the ramp, right? So this means that if you're using the ramp, you you're still doing the same amount of work, but this time the distance is 5 meters. And if the distance is 5 meters and the work is 1,000 Newton meters, what would the force be?
5,000. Wait, the work is 1,000, so you would divide by five
Hmm.
to get 200.
Yeah, say that again.
200?
Yep. So, what a machine lets you do, and an inclined plane is an example of a machine, a simple machine, is that it lets you perform the same amount of work with uh but you have to just input the amount of force that you have to input is far less if you're using the machine. So that's something called mechanical advantage, MA, and that could be like the force output over force input or distance input over distance output. So the force output is 1,000 newtons, but the force input would be, if you use the machine, would be what?
Um, 200.
Yep. And oh, and then this is just 5, right? And also, if you did the distance input here, which is 5 meters, over the distance output of just lifting this straight up, 1 meter, still 5, right?
Yeah.
So what this means is if you use this simple machine, the amount of force that you input gets multiplied by 5. Okay.
Okay.
Because you're conserving energy and but you're and if energy slash work is force times distance, if you increase the distance and you keep the work constant, the force would have to decrease, right?
Hmm.
So, yep, so that's mechanical advantage. Other examples would be like, or of simple machines would be like um a
I
lever.
was gonna,
Yep.
sorry, I was gonna ask about like a hydraulic press then, like if we can apply it there.
Yep.
Because I remember I've like gotten a couple questions wrong with those.
Yeah. Yeah. So you can have inclined planes, you can have levers, you can have pulleys, you can have hydraulic press. Even a screw, if you kind of think about it, is like an inclined plane
Okay.
because if you have, like the threads that are like diagonal and, when compared to like a nail, like let's say this is a nail, like a nail, you're applying, oops, the force straight into whatever you're nailing something into. Whereas the
Mhm.
threads of a screw are, as you twist the screw, start to enter into whatever you're trying to screw it into, like at an angle, like an inclined plane.
Got it.
Yep.
That makes sense. Okay. And then I guess I'm not sure if they're like completely the same concepts, but though I had another one also with a kind of like a free body diagram. Like they don't give you one, but um and like potential energy. I was kind of confused in this one.
Yep, yep. So okay. So that suppose that when an archer draws a bow by 0.1 meters, so we I mean, like, okay, for calculation problems, it's always good to kind of like start by taking an inventory of what we have. So we have, what's this?
The displacement,
Yep. And this.
the force,
Okay. So right away, we know if we wanted to, we can figure out what?
the work done.
Work and energy, right? So
Mhm.
all of the work performed on the bow is stored as elastic potential energy. Um, Now, do you remember what the formula for that is or was?
Is that 1/2 kv squared?
Okay, what?
V squared
Maybe.
or x squared? Kx squared.
Good. Okay. If the archer then fires an arrow of mass zero point 0.2 kilograms, so we have our mass here, vertically upwards, what is the maximum height reached by the arrow before falling back to the ground? So if you visualize this, right, it's like a person's like drawing, um, a bow and like shooting it straight up into the air.
Yeah.
What happens?
Well, initially it's potential or well, it turns into gravitational energy once it hits like the very peak of where it can go, and then it turns into kinetic energy as it falls back down.
Okay. So as it travels upwards, it would gain gravitational potential energy, right?
Mhm.
And it'll reach its highest point, right? And then start to fall down, right?
Yeah.
So why is that? Why does it, you know, reach a point, highest point, and then drop?
Um, because like there's like the force of gravity is outweighing the original force that was on the arrow. And so like the final velocity becomes zero until like the force of gravity pulls it down so much that it starts falling back down.
Yeah, so so this is a projectile, and a projectile is has only one force acting on it, which is gravity. Like, sure, you had some, you know, uh, you pulled back on it, like on the string or whatever, with a certain force, but once it leaves the bow, the arrow no longer has any force like from that original force, but right away it experiences the force of gravity, which means it experiences an acceleration, right?
Yeah.
Which then means that as it moves up, it's well, if it moves up with the velocity that's pointing up, the force and by extension, the acceleration is pulling it down. So the velocity that's moving up slows down or decreases until it hits zero, which is its highest point, And then it starts to fall, and this time the velocity and acceleration are in the same direction going down. And yeah, that's essentially why what happens there. So, okay. So now how could we solve this to find the maximum height?
One of the kinematics equations.
So let's see, right? Because what va variables would kinematics equations have?
Acceleration,
Uh-huh.
um, displacement.
Uh-huh.
I mean, I guess time, but we don't really have that.
Yep, and there's one more.
Velocity.
Uh-huh. So we don't have that, right?
Yeah.
So why don't we see what we do have? So what, yeah, I guess get from what we're given, what can we find out?
Well, I guess this is kind of where I was stuck on the question because I like remembered the elastic potential energy equation, but like because we had the K, I didn't know where to go from there.
Because we had the K or we don't have the K.
Like we don't like the equation has a constant that we don't have.
Yep, we don't have that, and we don't really have that either, right? Well, actually, this would be that.
Yeah, but then I was confused because that's not the like the overall displacement, right? It's just the displacement of
Yeah,
when you're pulling the bow back.
yep. But check this out. We have
So
force and distance. What can we do with that?
we can calculate the energy.
Yep. The work or energy, right? So so we could have so that energy when he releases the bow, um can turn into
Oh,
yeah.
yeah. So that would then turn into like gravitational potential energy,
Mhm.
which would be mgh.
Yep,
So we'd be able to find the maximum height with the mass that we were given if you set them equal to each other.
exactly. So a lot of times, well, there's going to be a lot. There isn't surprisingly that much like kinematic stuff on the MCAT. Like I actually very rarely see. Like maybe two of them I saw like from a blueprint exam, but
Mhm.
those problems you could also solve using conservation of energy. That's usually a lot more kind of like simple and um I see that a lot more often. So okay, yeah. So all right. Walk me through it. What can we do? How can we set this up?
Um, so we have the potential or the elastic potential energy, which would be FD cosine theta, but cosine theta would be one because it's parallel, like the or wait, actual.
Uh-huh.
So in this case, like you would still have a cosine theta. Oh, but the angle is zero, so it would be one.
Hmm.
Okay, so then that would be equal to mgh,
There you go.
and then you would just have to convert the mass into gram. Or actually, no, you don't because the acceleration is already in kilograms.
The mass you mean?
Well, or sorry, the field strength. Could
Oh,
you
G.
wait? I'm
Oh,
confused now.
oh, I see. You're talking about little g.
Yeah, sorry.
Yep.
Um, so the mass is 0.2 kilograms, and then G would be 10
Mhm.
newtons over kilograms, and then H would be the variable you're looking for. And yeah, you would just solve for that.
Uh-huh. So,
So
yep. So
that would be, oh, sorry.
you could, yeah, tell me. All right, yeah.
Well, we don't have to go through the calculation. It's more so just like setting things up. I get confused on, and I kind of get overwhelmed when I see um something like this, and I just like don't really know where to begin. Like a good strategy.
Got it. So I would say to visualize it, right? Like I'm
Okay.
really visualizing like someone pulling back on the bow and shooting it straight up into the air. And it's going up in the air until it reaches its highest point, then it falls down. And so yes, visualizing it really, really helps. And
Mhm.
then take an inventory of the values that they give you. And then, you know, equations and stuff should pop into your brain like FD. Well, all right, I can do work, right? Mass. I could also do like, well, gravitational potential energy. So yeah, okay. Now, do you, so you said it was like mostly a problem with setting it up, but do you get like, how are you with like the calculation problems, like in general?
Once I have the equation that I'm going to use in my brain, it's usually okay when I'm not timed. When I am timed, sometimes I make really stupid math errors that I wouldn't normally make.
Uh-huh.
And I think I need like I I was trying to organize my notes a little bit better when I'm actually writing things on paper because I tend to kind of just like write things wherever and then I get lost. Um,
All
so
right.
that happens sometimes.
Yeah, so I just want to see, so like how would you do the math here?
Um, it would be 300 times, or yeah, 300 times point 0.1 over zero point 0.2 kilograms times 10.
Okay.
Um, so 300 times zero point 0.1 is 30, and zero point 0.2 times 10 is 2, and then you get 15.
Okay. Now, okay, yeah, that works. That works. So,
Is there like a way that might be easier to do it? Like if I were to cross out like the 10, or I don't know,
yep,
a different.
do all those things. You can uh do that, and then this times this is that, and then this divided by the point two. But yeah, you did that perfectly. For other calculation problems, that could be more tricky. I can show you like some other kind of tricks and stuff. But yeah, excellent work. So yeah, we're just doing energy conversion here. Oh,
Okay.
I also wanted to ask, so that yeah, this what's that? What's this?
Um, I guess that was another thing I like skipped over the first time because I just saw that as like gravitational acceleration, which is not the case.
So
Um,
so that's the thing, like your whatever 9.8 meters per second squared, like if you remember Newton's second law, like it'll be F equals ma, but if we're talking about g, the acceleration would be little g, right?
yeah.
I could do again. divide mass on both sides to get this, right?
Yeah.
And this is in newtons and this is in kilograms, right?
Yeah.
Now, if you were curious how this all came to be, you know this equation, right?
Mm-hmm.
So this is between like 2 point masses, right?
Yeah.
Now, and these can be like the lines, like the field lines.
Mm-hmm.
Now let's imagine that this over here is Earth, and or let's say that M2 here is Earth, just because it's easier to see. And this light blue box, I'm gonna use that to zoom in onto the surface of the Earth, where these field lines are, coming down perpendicular. And now this is a uniform gravitational field. And if you plugged in for mass one or mass two or whatever, the mass of the Earth, and for the radius of the Earth, and big G is a constant, this turns into that 10 value, aka G.
And then would the other mass be like whatever object you're
Yep,
using?
yep. Because then this would be like the mass 2 times the little g, right? So what this means is, um, oops. So what this means is a 1 kilogram object will experience 10 newtons of force within Earth's uniform gravitational field.
Okay.
And the same thing is true so this is Coulomb's law, right? But if you had like, parallel plates with a uniform field within them, this can turn into capital E, which is our electric field. And that's going to be the newtons of force that you experience per coulomb of charge in a uniform electric field.
Okay.
Yep. So it's good to like have like intimate knowledge of the formulas to kind of see how they can be like derived from one another.
Yeah. I'm starting to get a little better with the formulas, but there are definitely some I still have to brush up on. And I
Yep.
think like what I was saying before with connecting ideas together,
Mhm.
um, yeah, I need help.
Yeah. Do you remember like if I did like the potential energy like using this, like it would be like over R instead of R squared?
Like for the
Mhm.
gravitational one.
Yep. It could also be for the electrostatic one, but it's okay. We can talk about that a different time. But all right, yeah. So let's go to the next one.
The next one, uh, yeah, fluids and pressure.
Hmm.
I guess I I'm trying to like remember what I was thinking during this, but I think I had an issue with what equation to use again because I was originally thinking Bernoulli's equation and then I got messed up with like all the variables um and didn't know like what to do there.
Got it. So, um, eh, what other type of equation can you think of that has like pressure values and stuff inside of it.
Um, some sort of like buoyancy.
Kind of. So like let's say, this is a container of water and this sphere is floating on top of the water. It's experiencing an atmospheric pressure, which is due to all of the air on top of it that gravity is pulling down, right?
Hmm.
Now, let's say that it's submerged a distance of like a depth of h. It's still going to be experiencing the atmospheric pressure because that's still on top of it, but it's also going to be experiencing the pressure of the water molecules on top of it, right?
Yeah,
So we can relate that to rho g h, right?
yeah.
Rho is going to be the density of the water, little g is little g, and h is that depth, right?
So anytime, like, are you ever going to be using rho GH by itself, or is it typically going to be seen with like the pressure of the atmosphere plus rho GH, like an example like this?
Uh-huh. So so the so so there's an equation called like that gives you something called the gauge pressure, and it might look familiar, but it's essentially this.
Yeah, I recognize the equation, but I'm kind of confused on like what a gauge really is and like how you like what you do with it.
Yeah, so like that would be like the pressure of this submerged object.
Okay.
Okay? So that's this formula. Now, again, the beauty with these types of formulas is that they all kind of, well, are derived from similar things. So what I mean is Bernoulli's equation, right? Um, do you remember what that was?
Um, atmospheric pressure, yeah, um, plus I'm guessing rho GH plus one. It was like some like one half rho V squared.
Okay. What do you think the 1/2 rho v squared represents?
Um, some sort of kinetic energy,
Uh-huh. And the rho gh?
gravitational potential
Yep.
energy.
So what the regular kinetic energy equation is this, right?
Yeah.
And the regular gravitational potential energy equation is mgh.
Mhm.
Okay. Now, check this out. If we divide this by volume, right? What's mass over volume?
Density.
Which is rho, right?
Yeah.
So if we divide this entire thing by volume, the 1/2 mv squared would turn into
One half rho V squared.
exactly. And same thing with the mgh, right?
Yeah.
So Bernoulli's equation is essentially conservation of energy, right? Per volume of like a fluid or something.
And then where does the other pressure variable come in to play with that?
Which one?
Like it, like in Bernoulli's equation, is it still the atmospheric pressure that you're also adding
Oh yeah.
to it?
So this is not gonna be like atmospheric pressure. It's just going to be whatever pressure like will exist in that system. I mean, sometimes it can be atmospheric pressure if it's like exposed to the outside. Um, but it doesn't always have to be that,
Okay.
right?
So what would be an example? Like, would this be an example where it's not, or it could be atmospheric, but
When you think
like what else would you use for?
this, you're asking about this thing?
Uh, kind of.
Mhm.
Well, that would be atmospheric pressure, right? Because it's open to the atmosphere. So then, what would be an example where you're using a different pressure?
Yep. So for this manometer here, I'm gonna say the pressure. I'm just gonna say pressure subscript L for pressure on the left side, pressure subscript R for pressure on the right side, and the left side is exposed to the atmosphere, and so it can have an atmospheric pressure here, right? But the pressure on the right is the pressure of the balloon, right?
Yeah.
So now if we used Bernoulli's, right, for the pressure on the left, the pressure value would be atmospheric pressure because it's exposed to the atmosphere, right? What would the velocity be?
0?
What's up?
Would it be 0?
Yep. Which means we can get rid of this term, and then guess what? We have that.
And so when you're talking about the velocity, it's the velocity of
The
the fluid.
Yep.
Okay. So anytime it's in equilibrium, you could get rid of that term.
Yep. So like the gauge pressure equation is derived from Bernoulli's equation. It's just that Bernoulli's equation would describe fluid dynamics, like the movement of fluids. But in this example here, we have a static fluid, so you can use the gauge pressure equation, but that still is really just Bernoulli's equation. But we have a static fluid, so the kinetic energy component will be zero.
Okay.
Right. So, okay. So pressure on the left, we can say is um well, okay. Let me start by asking you something like this. So if the levels of the mercury were equal, that would mean what would that tell us about the pressures, like the left side pressure and the right side pressure?
They would be equal to each other.
Good. And now let's say that the water level or mercury level is higher on the left and lower.
And the pressure of the balloon is higher than the atmospheric pressure.
Very good. So in this example, like the one that they give us, which is larger? I mean,
The atmospheric pressure.
yep, the pressure on the left, right?
Yeah.
And atmospheric pressure is what value?
1 times 10 to the fifth Pascals.
Good. And what would that be in kilopascals?
Um, 1 times 10 to the third, 10 to the second.
100 kilopascals, right?
Oh, yeah.
Yep. So the pressure of the balloon must be less than 100 kilopascals, right?
Yeah.
So if you scroll down a bit, we could eliminate some of these choices right off the bat, right?
Mhm.
Which ones can we eliminate?
A and B.
Yep, good. So that right there is just conceptually, we're able to, do that.
Hmm.
Now, the rho GH term is going to be so the thing that's a little kind of misleading here about this diagram is that like this we can say is like the height on the left side, and like this we could say is like the height on the right side. And what they're saying is H is really delta H, meaning like the difference between the heights.
Yeah.
So that means that so like and then also we would have to kind of choose a direction, meaning like if this height on the left is a decrease from the original height, we can say maybe that's positive, and then the height on the right is like an increase, we could say that that's negative. But you're
Hmm.
essentially going to then get like a rho gh with the h being like delta h.
Okay.
Um, but it's much easier to just do it conceptually. So we know that the pressure on the left is greater than the pressure, sorry, yeah, the pressure on the left is greater than the pressure on the right. And by how much is it greater? By, whoops, by this amount.
B greater. Uh, well, actually, it. So, are you saying you don't have to use H at all, or like you should still use it?
Yeah, yeah. So what I mean is we can either say that this pressure on the left is equal to the atmospheric pressure plus rho GH, or we could say the pressure on the right is your atmospheric pressure minus the rho GH term, right? Like the rho GH term is the basically like this like column of mercury. And that's the difference between, the left side and the right side. So, and this column is rho GH. So we could either say that the right side is the original atmospheric pressure subtracted by this, or we could say that on the left side it's the atmospheric pressure, but we add that.
Okay.
So, um, so if they're asking us to find the pressure inside of the balloon, aka the pressure on the right side here, it would be like this. Or sorry, it would be this, right? Which means 100 kilopascals for the atmospheric pressure minus, and then you'll do the math, like the 14,000 uh,
Yeah.
kilograms per cubic meter times G times H, right? So, yeah, what would that be, I guess, if you did the math?
Um. Well, 14,000 times 10 times like 5, so divided by 2. So like 10 divided by 2 is 5. Or yeah, I guess that's easier. Um, so 70,000. And then you would subtract that from,
Well, what unit is this? The 70,000.
it would be Newton. Hold on.
Mhm.
The 14,000 is kilograms per meter cubed. And then you're multiplying. So that would be newtons over meter cubed. And then you're multiplying by another meter. So meters squared, kilogram per meter squared.
Um,
Oh,
Mhm.
yeah. Kilogram or newton per meter squared.
You said newtons, yeah, per meter squared.
Yeah.
Is this any type of unit?
Yeah.
What?
Is that Pascal?
Yeah, fair word. So, and so we know that pressure is force over area, and newtons per square meter is a Pascal. So, so if we go back here, we have 100 kilopascals minus it's 70,000 pascals, right? Which is, yeah,
70
70
kilopascal.
kilopascals, right? That's up.
No, I just said 30 kilopascals.
Mm-hmm. Yep. Let's see the choices. Yep. Now, why do you think, um, so what the people who, the rough, like the 50% of people who chose B, what do you think they did?
Um, Added them together.
Uh-huh. Good. What about the ones who chose C?
Um, they messed up the conversion between pascals and kilopascals.
So,
So they subtracted by 7.
excellent. Good, good, good. Yep. So, yeah, you want to get to the point where not only can you get your wrong answer, sorry, not only can you get your right answer, and not only can you figure out which answers are wrong, but you can kind of see like the trap answers, I call them, like the answers that people will often get tricked into kind of choosing.
Yeah.
So, awesome.
Okay.
Yep.
Um, okay. Then I guess we could do the next thing. This might be a similar.
Mhm.
So, um,
Yeah. So,
well, I got that. First of all, I did the percentages wrong. Like, I don't know why I did it that way, but I wasn't sure like the difference between A and B, I guess.
yeah, so there's like, sure, there's a way to do it with like math, but there's also like the like rule of thumb for every, I think it's, yeah, for every 10 meters you are submerged, your pressure goes uh increases by 1 atm.
And is that just like something we should know, or okay, I don't
Yeah, because I mean otherwise, so if you scroll down, it seems like they're using like that gauge pressure value. Yeah, see this one? That's what
know.
called like the whatever gauge uh pressure, where we have atmosphere, and now this pH is, this is the rho, this is the G, this is the H, right?
Yeah, yeah.
So it's that formula that you can use. Um, but also, um, just a rule of thumb for every 10 meters, you go down, you go up by 1 atm.
Okay.
Mhm.
So I guess this one, um, I was confused how height and the velocity were related, like conceptually, without, I guess, using the equation.
So this is another kind of fluid problem that really is a projectile problem. So let's say that this person's on top of this like building of height h, and he has a ball and he like drops it, right? Now, at this initial position here, we're gonna do conservation of energy. So initial kinetic energy plus initial gravitational potential energy equals final kinetic energy plus final gravitational potential energy. So at this point, like, right before he drops it, what can you tell me about its kinetic energy and gravitational potential energy?
Um, all of its energy is stored in gravitational potential because he hasn't released the ball yet. So there's no kinetic energy.
Good. So that's out. And it falls, and, right when it hits the ground,
Then there's no gravitational potential, there's just kinetic.
good. So we have the complete conversion of gravitational potential energy into kinetic energy, right?
Yeah.
So, all right, let's use that, right? So mgh is equal to 1/2 mv squared. So I want you first to solve for the velocity.
Well, you could cancel out the mass and then it would be 2g or the square root of 2gh.
Excellent. Now, that's a final velocity. Now, this is a shortcut equation for any type of like this type of projectile problem where it's going from 100% potential, gravitational potential, to 100% kinetic. So this could be like dropping this ball. It could be like if you have an inclined plane, and once it hits, the bottom here, its velocity will be, uh, you know, determined by this formula. And then also like a spigot or like a faucet, the water that comes out of it will also obey this shortcut formula.
Okay.
Okay, so now,
So
yep,
so then is it not like a fluid problem at all?
correct. I mean, well, it's a
Technically.
station. Yeah, what's up?
Well, so like you were saying like a stationary fluid being converted into a moving. fluid.
Oh, so this is a yes, it's a static fluid, and this hole that the fluid comes out of, um, that fluid is subject to gravity and falls as if it was just, like a projectile, rather than it be like if you really are dealing with fluid dynamics, it would be like something like, oops, this or something, right? Like from so like that's the air. This is the area here, and there's a certain velocity there. Here, there's a smaller area, you know, which means a higher velocity. And up here, compared to down here, there's an increase in height. So that's fluid dynamics. Like when it's moving like within this kind of pipe structure. So for this question, though, it's not really moving, through like a type of like tube or pipe system. It's just that there's a hole and the water falls out of it exactly the way it does in a faucet.
Okay.
So,
But what about like
mhm.
what about the fact that there's kind of like pressure pushing against it? Like, does that not really come into play? Like, it just falls from gravity. It's not being like pushed out to the right and then you do you know what I'm saying?
so the thing is that the E that they wrote for velocity, that's let me ask you this. So like let's say that a person is holding a gun and with one hand, and the other hand's holding like a bullet, and they're at the same height, and he fires the gun and drops the bullet at the same time. Which bullet will hit the ground first? The one he drops or the one he shoots?
They both hit the ground at the same time.
Good. So, and that's because of what reason?
Gravity.
Uh-huh.
Yeah.
And yeah, go on. Tell me more.
Um, well, the fact that they're both at the same initial height and gravity is acting on them. So,
Gravity.
and they, yeah,
Yeah, go on.
yeah, they're the same mass also, but that doesn't, I don't think that matters.
So the gravity is only going to be in that vertical dimension. So the only thing, which means that the gravitational force will be vertical, which means the acceleration due to gravity will also be vertical. So the bullet fired by the gun has a horizontal velocity as well, but gravity isn't act can't act on a horizontal direction, so the horizontal velocity won't change. Um, but it's vertical velocity will change, right?
Okay.
So in this question, this uh the pressure um is what makes this water come out sideways with a velocity that's sideways because of the pressure, right? Because otherwise, like this spigot or faucet here, it should just fall straight down,
Mhm.
right? So yeah, the pressure contributes to the water or whatever moving to the right. Uh,
Okay.
yep. So,
So
um,
then what would you
mhm.
do, like, what would you do after, like, when, to answer the question, like, if you're trying to find the height?
Oh yeah. So basically this, but you just solve for the height now.
Okay.
Mhm. But yeah, this equation, remember it for anything like any complete conversion of potential to kinetic. So guy dropping something from a height, um, the final velocity of some box as it hits the ground from the inclined plane, and then water coming out of the spigot.
Take a screen.
Yeah, yeah.
I like I was trying to answer this question logically based off of the given equation, but they were using the Lorentz equation, and I like completely missed that part.
So let's talk a bit about magnetism, right? So yeah, what can you tell me about magnetism? I know that's a vague question, but
Um, well, I guess between two point charges, if one is positive and one's negative, they'd be attracted to each other. And if they're the same, they would repel.
so is that magnetism or is that electrostatic like force?
Electrostatic.
Uh-huh.
Magnetism. Does that have to do more with like a field?
So your um yeah, so the first thing you described was yeah, electrostatics and uh but if you have a moving charge, it will create or be sensitive to a magnetic field. So,
Okay.
and now that's true for a photon as well. So, what I mean is, I have a like a GIF. Oh, here. Okay. Okay, I put something in the chat. See it?
Yeah.
And it's like moving, it's like animating.
Yeah.
So this is along the z axis here is the direction of a photon, and in the y direction, it's making an electric field in blue. And in the, oh wait, I read that wrong. The x-axis is the direction of the photon, and the y-axis is the direction of the electric field that's in blue. And in the z direction is your magnetic field. So also, like if I use my pen, so let's say this pen is in the direction, is the direction that a photon is moving. Uh,
Mhm.
Perpendicular to that will be an electric field, and then perpendicular to both will be your magnetic field. Okay.
Okay.
And so once we start talking about, oh, and then that's why, so what's electromagnetic radiation?
Um, when a like particle or an electron bounces off of something, and it like gives off a photon of energy.
So it's basically just light, right?
Okay. Yeah.
And that can include visible light that we can see. It can include UV light. We can include X-rays. It can include gamma rays, right? Radio waves, um, infrared, all that stuff. That's light. And but it's also called electromagnetic, radiation or electromagnetic waves because when a photon moves, yeah, it produces an electric field as well as a magnetic field.
Okay.
Now, due to the nature of magnetism being in three dimensions, it means that we can use the right hand rule. Do you remember that?
Yeah, I was gonna ask you about that because I know there's like two different right hand rules you can use, and I get them really mixed up
Yeah.
of which one is which.
Yes. Uh, so the standard one is when you keep your hand like straight, like a karate chop, and your thumb is going to be in the direction that a charged particle is moving.
Hmm.
So I guess I can start by writing the formula. So it's Q VB sine theta, and it has a sine term in it. What can that mean?
Th that it's perpendicular.
Yeah, yeah, good. Um, and then what's the Q for? What's the V for? What's the capital B for?
The C is the Q is the charge, and the V is the velocity of the charge.
Excellent. Great job. So so the right hand rule, that's like a karate chop. Your thumb will be in the direction that the charged particle is moving. Your like these fingers will be in the direction of the magnetic field. These fingers.
Okay.
And then your palm will be facing the direction of the magnetic force.
Okay. So there's no C, like you can't really do this speed. Like you're not using speed.
Uh, sorry, what are you saying?
Like, sorry, in the like when you're using the right hand rule, you're like looking at the force as one of the variables rather than the speed, like the velocity.
The speed or the velocity that it's moving was going to be the where your thumb points.
Oh,
Mhm.
so you're not using Q then because it's just the point.
Yeah, like you're still using Q when you use your formula, but um, since Q is just charge and that's not like a vector, you know what I mean?
Yeah.
Whereas velocity is a vector, which means it has a direction, and magnetic field is a vector, which means it has a direction, and force is a vector, which means it has a direction. So that's why we use the right-hand rule for those vectors.
Okay.
Um, but yeah, you do need the charge, of course, but it doesn't play a role in the right-hand rule.
Okay.
Right-hand rule is just to show you the direction of some of the things. Not any like, calculations or anything like that, right?
Yeah.
So, okay, so that's that right-hand rule. The other one is when you do the curl. So like if I had a wire with a current moving up like this, I can put my thumb up to be in the direction of that current, and I can curl my other fingers, right, into the page or into the screen on the right side,
Mhm.
and then it circles around it and then comes out of the screen on the left side, right?
Yeah.
So that's the curling kind of right hand rule.
And that's representing what? Like when you're curling, that's what is that represent?
Yeah, the magnetic field.
Okay.
The
So
X,
there's only two variables for that one then.
correct.
Okay.
Yep, the X's mean it's going into the page, and the dots means it's coming out.
Okay.
Okay, so now let's say we have a magnetic field that's going into the page, and let's say we have a charged particle that's not moving. Um, what will happen?
Um, the magnetic or the charged particle will like have like field lines coming out of
So let me start by asking this. So by the way, so okay, this is an electric field, and electric field lines go from what to what? Oh, I didn't hear you.
a positive charge to a negative charge.
Good. So if this stationary uh charge here is in this electric field, what would happen?
It would move to the right.
Uh-huh. And that's because of an electrostatic force, right?
Hmm.
All right. Now, what about this stationary charge in this magnetic field?
It would be coming out of the page.
So for this one on the right, we essentially did, something like this because a force is causing, because okay, if you take a stationary thing and you get it to move, there's an acceleration, right? Because you're going from velocity of zero to velocity of something greater than zero. And if you have an acceleration, you have to have a force, a net force, right?
Yeah.
Okay. Now, for this stationary charge in this magnetic field here on the left, it must, if it is to move, it must have, it must experience a magnetic force, which is expressed by this formula. So, what could happen here?
So be perpendicular to
What's its velocity?
zero.
So,
So
say,
there's no force.
mm-hmm. Which means,
So so the charge can just like even though there's a magnetic field, it doesn't necessarily have to like exert a force onto the charge.
correct.
Um,
So this will just stay stationary.
okay.
Okay, now what if it's moving in this direction? Tell me what well, now it has a velocity, so it will have a magnetic force, right?
Yeah.
Okay. What direction is that magnetic force going to be?
Um, well, the velocity is moving in this direction, and then the magnetic field is into the page. So
Hmm.
the force would be up upwards.
Good. So this will kind of like move like kind of diagonally like this, right? Okay. Now, where's the magnetic force pointing here for this one?
Uh, the magnetic force,
Mhm.
like up, up,
Mhm. Uh, use the
or like how is that different from what we just did though?
um. Well, you're still using the right hand rule. So tell me now, because the
Oh,
velocity.
like once the particle is like over there.
Oh yeah, yeah. I'm talking about this one. Yep.
Oh, um, well, the velocity is I in towards or up,
Up. Yep.
and then the magnetic field is in,
Uh-huh.
so the force would be to the left.
Good. So it'll move around here. What about now?
And the force would be down
And here.
to the right.
Any pattern here?
Yeah, it goes in a circle.
So this means that, well, that this is a centripetal force or centripetal acceleration, right?
Yeah.
And the formula for that is mv squared over r.
Mhm.
And we can equate it to the magnetic force, right?
Yeah.
Okay. Now, this question's essentially asking that. It's saying when a positively charged particle enters a magnetic field perpendicularly to the direction of the field, it moves in a circular path due to the centripetal force given by mv squared over r. And what changes to the magnetic field strength and velocity of the particle would produce a decrease in the radius of the particle's circular trajectory.
Um, so you could set the forces equal to
Yep.
one another and then solve for R,
Good.
which would be like QVB sine theta over MV squared, or the other way around.
Wait, what's up?
Like if you set them equal to each other, then it would be MV squared over QVB.
Oh, sorry. Okay. The step after this, you're saying. So, yep. MV squared over QVB. Yep.
Um, so then if you want to decrease the radius, you would have to,
Well, this would cancel, right?
oh yeah.
Okay.
So then be MB over QB. And if you're decreasing the radius, you would have to decrease the mass, or you would have to increase the magnetic field
Hmm.
or the charge.
Okay.
So then that would be B, like for the answer.
Yeah, decrease in velocity and an increase in magnetic field strength.
Okay. So then
Hmm.
on on the actual exam,
Yep.
I guess like I understand everything now, like that we've talked through it, but I like get worried that I'm not going to be able to like visualize it like that when I get a similar question. So
What-
like what would you
Yeah.
like advise I do to
What
help visualize?
you can't visualize, like visualize what aspect of it, I guess.
I guess because it was talking about how like the charge is entering the field perpendicular and like we were drawing out the diagram for it.
Okay.
I think I would just like I can kind of I know myself and I'd kind of get like stressed out and not be able to visualize what they're talking about.
Uh-huh. So, okay, let's see. So they're saying that um, a positively charged particle enters the magnetic field perpendicularly to the direction of the field. So what I drew here was, its velocity being like I initially drew it to the right, but and I drew the magnetic field going into the page, right? But it could have also just been, the circles to mean magnetic field out of the page.
Yeah,
I could have drew this with the velocity going to the left, but the velocity and the magnetic field is still going to be perpendicular, right?
yeah,
So, yeah, basically that. So I think, um, yeah.
okay.
Oh, and that's also how a mass spectrometer works.
Yeah, I guess I was a little confused on that too because I was confused on how the centripetal force came into play with that. I mean, it makes more sense now. Um,
Oh yeah,
but yeah.
let me ask you. So, how much work is the magnetic field doing on this charged particle?
Well, since the particle is moving, then it would be like the force times the distance it moves, I guess.
Okay, keep going.
Um, the force times the distance times the like the cosine theta.
Okay. Yep.
Um,
And what would theta be?
well, cosine 90, which is 0, so it would not be doing any work.
Yep.
Okay.
Now, what would what would happen to the would it cause a change in velocity?
Because there's um well the force is the same, Like you're not changing the magnitude of the force, so you're not changing the velocity.
So, um, is velocity something that is just a magnitude, or does it have a direction as well?
It has a direction.
Okay. So is this velocity changing directions?
Yeah,
So it is changing velocity, right?
yeah,
Is it changing speed?
no, because speed doesn't have a direction.
Good. Is it changing kinetic energy?
It's changing the no because it's velocity squared.
Yep. So if it's changing direction and we have negative velocity and positive, when you square them, you get rid of that. So, so yeah, there you go. So basically, um, I guess the key takeaway here is, I mean, aside from, um, the right hand rule and aside from the fact that a magnetic force must operate on a moving charge. But in addition to all of that, that moving charge within a magnetic field will move in a circle and maintain its kinetic energy. But yeah, just go moving around in a circle.
Okay.
And since this radius term is also proportional to